Okay. Okay, so yeah, hello everybody. So as promised, today we're gonna talk about equivariant chemology, and in principle, this is a topic a little bit apart, but of course we'll make a lot of contact with the symplectic story which we were developing up to now. Today we're gonna see it a little bit towards the end of the class, and next week we're gonna see a lot more of it. And probably the topics will fully merge in the class in 2 weeks from now. But and today also I will start with some kind of a little bit of topological background on equivariant chemology. Don't take it too seriously in the sense that it would require maybe a full-fledged course. So I just give you a little bit of impression on what it is and how it works. That's because these are real definitions of equivariant chemology, but that's not those that we're going to use in the course. So somewhere around the middle of the class, we're going to switch to some other approach. You will see which uses differential forms, and that's the approach, the Henri Cartan's approach that we're going to be using for the rest of the course, and that's the one which is used in applications to moment maps. All right, so what is the setup? As usual, we have G, say a compact connected Lie group, and here is the following definition, which plays an important role in the story. So EG is a space acted by G and is called the universal G bundle if there are two conditions which are satisfied. First of all, well, since it's supposed to be a G bundle, you want the G action to be free. And then the second condition, which sounds a bit surprising if you've never seen it, you want EG to be contractible. So then if you have such an EG, so then we have a space which is called BG, which is a quotient of EG by that free G action. And this is called a classifying space of G bundles. So let me give you some standard facts from topology books about this setup, and then maybe just one example which might clarify a little bit roughly what we are talking about. So here is a list of facts. You know, there are different approaches to building those EGs, and in some way EG is not unique. So there are many spaces which may pretend to that role, but EG is essentially unique up to G equivariant homotopy equivalence.
So actually, I have this question. So would it be appropriate to say it's the universal G bundle? I was asking.
Yeah, that's a little bit of a question, right? I mean, it depends on how you read that comment, right? So EG is in some way unique, but still it has many models, right? So those models are G equivalently homotopy equivalent. Mm-hmm. But I mean saying the universal G bundle, I think it depends on which category, in which category your articles are
For
positioned.
goodness sake. Okay.
So,
All
yeah,
right.
I mean,
All right.
this
Fine.
might be spaces which look very different, those EGs.
Yeah.
So that's why I cautiously, right here, there is a kind of grammar math.
No, that's not what I meant at all, Anton. I was honestly trying to understand to a degree of uniqueness. So I mean, this.
Yeah. So it's not unique, but it's unique up to in some category, right? So if you consider that G-equivariant homotopy equivalences are isomorphisms in your category, then it is unique. But I mean, you know, homotopy equivalence can do lots of things to your space. So that's why I'm putting it that way. So then BG is unique up to homotopy equivalence. So then there is yet another fact. So suppose we take some space, let's say B, and we consider a map from B to BG. So then we can arrange a principal G bundle over G. So by the pullback construction, right? Over BG we have so E is equal to phi star of EG. So this is a G bundle over B, and let's say if we denote by pi this projection, and here we denote, let's say somewhere by P the projection from EG to BG, so then the fiber over B is by definition equal to the fiber over the image of B. So, and it turns out that all principal G bundles are obtained in this way. So, I mean, one shouldn't estimate the usefulness of this construction. This is a somewhat theoretical construction, but nevertheless, that's why you have those classifying space story. Maybe even a little bit more precisely. So suppose you have G bundles over B. So G bundles up to isomorphism. And then this set is isomorphic to homotopy classes of maps from B to BG. Homotopy classes of maps. So as I say, these are just some, up to now, this is some kind of extract from topology books. Maybe now a relatively concrete example. I had second thoughts to put some more examples in the problem set, but who knows? Maybe I'll save it for the next one. So let's say G is equal to S1. So then one possible model of EG, of ES1, is a so-called infinite dimensional infinite dimensional sphere. And so this infinite dimensional sphere is the set of sequences of complex numbers. So Zi is in C, and it is not equal to 0 only if I is in some finite set. So in each sequence, there is only a finite number, of non-zero Z's. But, and they can be, of course, different in different sequences. And then to be a sphere, right, this infinite sum, which is actually a finite sum of squares of absolute values, should be equal to 1, right? So this is some kind of space. It's infinite dimensional, and it has an action of S1. So you just rotate each of those Zi's. Since we have this condition, right, that the sum of squares should be 1, there are always some non-vanishing Zi's, right? So so this means that this is a free action. So if at least one Zi is non-zero, then at that point the action is free, and there is always some non-vanishing Zi. Now you can think about it in the following way, right? That so there is a one-dimensional sphere sitting inside a three-dimensional sphere, sitting inside a five-dimensional sphere, and so on, where S, let's say, 2k minus 1. So these are sequences which stop at zk, and then which continue with zeros. Right, so this is a subspace which is just isomorphic to a finite dimensional sphere, to a unit sphere. So now so the claim is that this S infinity is actually contractible. So I'm not going to prove it, and if you want, you can look up proofs in the literature. They are quite nice and beautiful, but more or less, like in the first approximation, why this is true. This is because S2k minus 1 inside S2k plus 1 is contractible, right? And that's intuitively clear. Now, kind of all of your points, they are sitting in one of those spheres, but in the next sphere, that previous sphere is contractible. So of course, one should still work a little bit to make this argument precise, but it's easy to believe that this S infinity is contractible. So you see, that's an example of a classifying space. One cannot say that, I mean, probably a professional topologist would be happy to work with it. It's not something that we want to work with in this course. But let me still continue a little bit along this more general line. So, so let's also look at BS1, right? BS1 in this model should be ES1 divided by S1. And if we look at this sequence, right, every time we divide an odd dimensional sphere by the S1 action, we get a projective space. And so this is called CP infinity. And the corresponding sequence is CP0, which is a point. That's when I quotient this S1 by the S1 action, and it is sitting inside CP1. It is sitting inside CP2, and so on. Perhaps one small remark about this setup, which will be useful for us later on. We know that the chemology class of the Fubini Study 2 form, right? It's sitting in H2 of CPN for any n greater or equal to 1. And it turns out that those embeddings here, CP1 into CP2 and so on, they respect this generator, right? So chemology of each of those CPNs, they have that generator, omega Fs, and if you pull back on the natural maps, which we have here, those generators will all agree. Well, so in CPN, because of the dimensional reasons, so the n plus first power of omega Fs is 0. That's simply because of the dimensional reasons, right? So if you take the 2n plus 2 power, the 2n plus 2 graded component of chemology of CPN, it is simply 0. In fact, more is true. So the whole chemology ring of CPN, let's say over R, we're going to be working mostly over R today, is isomorphic to R of this generator omega Fs divided by this relation. So that's the chemology ring of CPN. So here is the fact, which is not that surprising, and that we're going to recover in this other approach later on today. So the chemology ring of CP infinity is simply equal to the polynomial ring with one generator that I now call omega Fs, but that we're going to call in a different way later on. And the degree, of course, of this generator omega Fs is equal to 2. Now it's not very surprising, because 2 is the degree of a symplectic form, in particular of the Fubini Study form. But later on it will be somewhat less obvious. So, but now we're kind of prepared that some kind of generators of polynomials which are somehow set in degree 2. So that's something that we should not be too surprised about later on. So now maybe the central definition of the equivariant chemology theory. So, so we have G acting on M, and we associate, as usual in chemology theory, right? We have some geometric setup. So here G acts on M, and we associate to it some abelian group, graded abelian group, so which is called AG of M. So this is G equivariant chemology of M, and this is equal just the ordinary chemology of the space M cross over G EG, where this is a quotient bidiagonal G action. Note that this diagonal G action is necessarily free, right? Because it's already free on EG. So on M, it can be free or not necessarily free. So now what's the structure of those equivariant cohomology theories? So we associate to a G space M this gadget. At the moment, it's very difficult to say what it is. But now, first of all, let's consider the trivial G action on a point, right? So then HG of a point, by definition, is what? Is H of EG divided by the G action, right? Now there is no M, but EG mod G, that's BG. So this is the cohomology of BG. So that's one fact. So now in equivariant cohomology theories, cohomology of a point is a kind of non-trivial thing. So that's strange, unusual, and sometimes very, very useful. We'll see how useful it is. So now maybe one more fact or one more idea. So this space, this product of M and EG divided by the diagonal G action, it has a special notation, MG. And so there are several maps from MG to various other spaces. And in particular, there is always a map to EG mod G, which is BG, right? So we just forget the M part. So like, so these are now the set of pairs modular the G action. Well, let's forget the first element in the pair. So we get a map to EG mod G. And this means that in cohomology, H of BG, which is the equivariant cohomology of a point, maps into cohomology of MG, which is by definition the equivariant cohomology of M. Right? So this is an algebra homomorphism, right? And as a consequence, HG of M is a module over this HG of a point, right? You map HG of a point into M, and you just multiply, right, things by those images. So this gives you an action of HG of a point on HG of M for any M. All right. So more stuff. Right. So so we said that MG. We said that MG, there is a natural map to BG, right? That we just described. Now, what's the fiber of that map? Since we're dividing here by G, the fiber of that map is simply isomorphic to M itself. So from that, we conclude that there is a natural map from HG of M to the ordinary cohomology of M. So you can forget about equivariance. So that's also some natural construction, and you will see how it plays out in exercises. Maybe here there are two remarks about it. So first of all, sometimes it happens that the equivariant cohomology of M is simply equal to the tensor product of equivariant cohomology of a point and the ordinary cohomology of M. So it's not always, but sometimes such things happen. So, and then in this case, we say that M is equivariantly formal. So this is just a word for it. So you will see examples of such situations in the problem set. And maybe let me see. I wanted to give you one more thing. Okay. So yeah, maybe if I recall it, I will return to it. So, and maybe the last kind of general theory discussion that I wanted to mention. Suppose that, sorry, yeah, now it comes back. Right, okay. So in general, we're not going to be develop it now, but we're going to use it later on. Suppose that you have a subgroup H of G. Say a closed, let's say closed, connected fully subgroup, just a nice subgroup. So then one can always go from G of M to H of M. So this is like a more general story than the one that we have here. And maybe just to give you a hint why this is true. So suppose we have an EG, right? So the action is free and EG is contractible, right? So that's the definition. But then, of course, H, which is sitting inside G, it also acts. If the action of G was free, the action of H is also free, right? And EG was contractible, well, it remains contractible. So you see, like that's the story about uniqueness. So EG is actually also an EH, right? So G, right? Because I wrote something else. Yeah, okay. Now that's fine. Okay. It says that my connection is not sufficiently stable, but yeah, let's hope for the best. So EG is also, you can use it as a universal bundle for H bundles, right? So that this shows that it's not really unique. So you can use that to construct natural maps from G equivariant cohomology to H equivariant cohomology. Right. Now maybe the last thing I want to tell you from the general theory. So suppose that the G action on M is also free. So then from Mg, which is M times Eg divided by the diagonal G action, you can also construct a map to M mod G. Now M mod G is also a good space, right? And this would mean that we have a map from cohomology to M mod G to G equivariant cohomology of M. And it turns out that this map is an isomorphism. So in that case, if M carries a free G action, so then the equivariant cohomology of M is simply the ordinary cohomology of the base. So that's kind of an interesting fact. And you see, so this is a kind of opposite situation to the situation of equivariant formality. So equivariant formality says that this is a free HG of a point module, right? Because, yeah, we have, say, we can choose a basis, the basis of H of M. So if M is sufficiently nice, H of M is finite dimensional, and then we just tensor multiply by Hg of a point, and we have a free module of Hg of a point. But here, what happens, right? We have H of M mod G, and you saw that Hg of a point, right? Our only example up to now, that was this polynomial ring. So in that polynomial ring, right, we kind of, how would it act, that generator? And it turns out that here, the action of Hg of a point is trivial, which means all generators of positive degree act by zero. So these are two very, very opposite, let's say, opposite situations. So the equivariant formality and when the G action on M is free. All right, so as I say, don't pay too much attention to this part of the class. I think it will be useful for you later on when you want to better understand what's going on in more concrete calculations. It gives you some kind of guideline. But now we pass to a very different story. So let me call it so Cartan model of equivariant cohomology. And so here I will state the main theorem of today's class. And it tells you how to compute the equivariant cohomology in some particular situations. So our situation will be as follows. So we now going to assume that M is a manifold. And we'll be interested. So we'll denote it still Hg of M, but we'll always be discussing the equivariant cohomology with real coefficients, right? So these are two assumptions of Cartan's theory. So then there is the following famous theorem of Henri Cartan. Which says the following. So this equivariant cohomology with real coefficients can be computed as a cohomology of the Cartan complex with respect to the Cartan differential, where the Cartan complex and the Cartan differential are built of differential forms on M. So what are those gadgets? So this Cg of M these are differential forms on M. Tensor multiplied by what is called the symmetric algebra of the dual space to the Lie algebra. And we take G invariants under the diagonal action. Diagonal action. And here maybe just also to simplify things, and we're going to use it later on. So the symmetric algebra of G star, this is the same as polynomials on G. So that's just the same gadget. So we're considering differential forms on M, which are also polynomials on our Lie algebra G, and then we take G invariants under the action on differential forms and on polynomials. So that gives us some kind of graded vector space. And for the gradient, we are saying the following. So maybe so CG of M, let's say K, is equal to the direct sum omega I M times Sj G star, where I plus 2J is equal to K. So those generators of G star, whatever they are, they have degree 2. So you see now, maybe you see better why I wanted to show you that geometric example with the Fubini-Studi form, right? It's actually, it comes from there, but okay, so that's part of the Cartan's theorem.
Why do elements of G star have degree 2? Is that
right? I mean, that's, well, let's say the first answer, which is not very informative, that's because that's the Cartan's theorem, which tells us that. Now, slightly less formal but more informative answer, that's because, right, we see that this hg of a point, it plays the major role, right? And we saw what is hg of a point, or the cohomology of the classifying space, in one example. And in that example, which is here, the cohomology of the classifying space is a polynomial algebra with a generator of degree 2. And here we actually know why it is of degree 2. That's because the Fubini-Studi form is a symplectic form, and symplectic forms are of degree 2. So that's the general source of this degree 2 story. Right. Okay. So now, what is dg, the Cartan differential? So that's the de Rham differential on differential forms plus, and here let me write it down and let me explain. So here, kind of one can, it's an invariant object, but it's more convenient to write it down in terms of a basis. So, so here I decided to choose a basis, EA, the basis in our Lie algebra G. Then, as usual, EAM are fundamental vector fields, right? So fundamental vector fields. And those set A. So this is a dual basis. Right, so what you're doing, you are contracting with a fundamental vector field, and you're multiplying the polynomial part on the corresponding generator of G star. Now maybe just a sanity check. So what happens with the degrees, right? So the de Rham differential adds +1 to the degree of forms, and identity is of degree 0. So the degree here is +1. The contraction subtracts 1 from the degree of forms, but each generator of G star has degree 2, we decided. And so this also gives +1. So you see, you can say maybe that's another reason. The differentials, normally they should be of degree +1 or -1, depending on your convention. So here, those xi's, they need to have degree +2 if you want to have some kind of consistent cohomology theory.
Yeah, that also makes sense.
Yeah, I mean, let's say that's a circumstantial evidence, but so now maybe I make the following. Perhaps I make the following short comment about.
Presumably we. I mean, I don't know. Is we're going to show that d squared is 0? Is that?
Sure. In a second.
Yeah.
In a second. Yes. We're going to show that d squared is 0, but let me first make a remark. So here is a remark. So as I said, again, this symmetric algebra of G star, that's a somewhat abstract notion. Perhaps it's better to work with polynomials on a Lie algebra. So let's say, let's use this isomorphism. Sorry, as G star is the same as polynomials on G. So then what we can do, right? We can say that elements of CG of M, right? So these are polynomial maps from G to omega of M, which are invariant under the G action. So these are polynomial maps. So then what will happen, right? We can think now of an image of such a map at some element X in G, right? So this X is mapped to a form alpha of X in omega of M. And dg of alpha as a function of X will look as follows. So this will be d de Rham of alpha plus, and here you see what's going to happen. So those psi a's, right? So these are functions, linear functions on our Lie algebra, right? So which map X to the pairing psi ax. So and then we also know that X, let's call this thing XA. So this is just XA times EA, right? That's just the decomposition of X under the linear basis that we chose. So why I'm saying that, that's because the second term, which looked a little bit complicated and mysterious, it just transforms into the contraction with the vector field XM, right? So here EA times psi A is actually our X, and we contract with that vector field. So that's in most cases, that's what we work with. So now a proposition, as Ian predicted, it probably good.
Sorry, those things are still their functions of x on the right-hand side.
Yeah, they are functions of x, absolutely. They're still polynomial functions of x, right? Alpha was a polynomial in x. Maybe we can also write it here. And iota x of alpha is a polynomial of x, where we raise the degree by 1 because iota of x is a polynomial of degree 1. Yeah, we'll see it now in more concrete examples. So we're slowly getting there. So it's getting more and more concrete, right? We started with some abstract nonsense. Now we have almost understandable formula, and we're going to work with it let's check that d square is 0, and then we'll see an example. So proposition dg square is 0, where, of course, on CG of M. So here is a proof. That's one of those important one-line proofs. So, well, dg square, let me write it in this form that we just had. So ddram plus iota of xm squared. And this is equal to ddram squared plus iota of xm squared plus ddram iota xm plus iota xm ddram. Well, so this is 0. This is also 0 because if you contract with the same vector field twice, you get 0. Finally, this guy is by Cartan magic, is L of xm. But remember what happens, right? So L of xm now acts on CG of m, right? And on CG of m, what does it do? So it should act on differential forms, and we can imagine that it acts on the Lie algebra argument, but the Lie bracket is skew-symmetric. So if you try to rotate x by the adjoint of x, you get 0. So therefore, Lx of m is actually 0 on CG of m. So that's actually. So that's why the differential vanishes. I invite you to do the calculation in a more formal setting offered by this formula. So of course we are supposed to get the same, but I mean would be good to check it explicitly.
In that formula, in the line above that formula, is it? If you just look at that, the line above that formula, should there also be a G invariance?
Oh yeah, sure.
In the green formula.
Yes, that's right. That's right. Yeah, everything is G invariant. Otherwise, for instance, we see that otherwise, if you don't have G invariance, then the Cartan's differential would not square to 0, right? Maybe now one more remark. And that's actually an important remark for us. Suppose that our group is abelian. So suppose that this is a torus. So then this story sort of simplifies. So CT of M will be what? Now you see the G action doesn't act on polynomials because the adjoint and coadjoint actions are trivial. So then we just simply have invariant forms times those polynomials, right? So these are polynomials on T. Right. Okay. So let's do the following. I would like to do one. Yes.
What is the zeroth cohomology of this differential?
You mean what is H0? Let's do an example.
Yes.
So I plan to do an example, compute like all the cohomology of something. So the example is very, very simple. So we look at S1 acting on itself by translations. So this is M, and this is the action by translations. So in particular, right, we know the answer from general theory, right? Let's just write it down, and then we'll see how it works in the Cortan's model. So we are supposed to have H of S1 mod S1, which is H of a point, right? And then, so this is R for degree equal to 0, and this is 0 otherwise, right? So that we actually know what it is. Now let's see what Cortan's theory is telling us. Maybe the first thing, just to make sure. So H S1 of a point, right? Now this is simply equal to S of Li of S1 star, right? So the symmetric algebra of the dual. Now this would be the same as R polynomials in one variable. Let me call it X, and the degree of X is equal to 2, right? So here I'm just implementing this story. So if there is no M, this Cortan differential is 0, and so we're getting the polynomial algebra that we already encountered in the geometric approach. Okay, so now what happens with our example? So the Cortan model, so those chains CS1 of S1, right? So these are S1 invariant differential forms. Tensor this polynomial algebra, right? Now S1 invariant differential forms on S1. So that's very easy, right? So these are, since they're S1 invariant, the coefficients are constants. And there are differential forms of degree 0 and 1. So here theta is a natural angle coordinate on the circle. So d theta is the volume form, and here A and B are in R, right? So these are the forms. Now, how does the Cortan's differential act? So the Cortan differential is d dRAM plus X times the contraction with the fundamental vector field. Now there is only one, and it is d over d theta. Right now, the basis of Lie algebra consists of one element. There is a dual element which I call X now, and that's how it looks like. Now let's apply. So this ds1, let's apply it to A plus A plus B theta. And here it might be slightly more convenient to think that those A and B are polynomials in X, right? So now I'm putting together this gadget and that gadget, right? So A and B were constants, but actually I should tensor multiply by polynomials of X. So I can also put this polynomial dependence in A and B. And what do I get? So what do I get? So the Durand differential simply vanishes because everything is constant. And this second term, it only acts on the volume form. So I'm getting X, B of X, right? So that's what I get. So now maybe let's see, let's write a basis of this space. So let's say basis, the linear basis of C S1 of S1. We can just write it down, right? So we have, let me write it in the following way. So there is 1, X, X squared, and so on, right? So this is what was different components of A of X. And then there is, let me write it in this way, d theta, X times d theta, and so on. So the degrees are equal to 0, 2, 4, and so on. And here 1, 3, and so on. So, so these are even and odd degrees. Now, each of those degrees in our complex is simply one-dimensional. Now, we just proved that what this Cartan differential is doing, it is mapping d theta to x, x d theta to x squared, and so on. So this shows that cohomology vanishes in all degrees but 0, right? Because that's the only thing which is not killed by the differential, and that's the only thing which is not mapped to anything non-vanishing by the differential, right? So here, just by inspection, right, what we see is that H0 S1 of S1 is R, and HI S1 of S1 is 0 for I greater or equal to 1. So how is it? Is it like now more or less understandable what's going on? So I take it as yes.
I just wanted to understand what are the zeroth cohomology, because usually people talk about cohomology as derived factors of some duration.
Yeah. So the zeroth cohomology.
Yeah, it's okay. In the example, it's clear, but what
for any connected manifold, as usual, that will be always the case. It will be isomorphic to your basic field. The zeroth cohomology. The zeroth equivalent.
So it's not so here we shouldn't think about cohomology as derived factor of something. It's not productive, or what?
Yeah, I don't know. Maybe I don't know enough of derived functors to tell you how productive it is. But you see, this is a relatively maybe. I can think about the more convincing answer for the next time. But you see here, one of the ideas of the definition of equivariant cohomology is that we are saying we want to associate something to M with a G action. And we reduce it to the ordinary cohomology theory to some space which may be whatever, not very convenient to work with, but still, right? We take this M cross G, e.g. This is now a space or a class of spaces up to homotopy equivalence. And we're just declaring that the equivariant cohomology is the ordinary cohomology, whatever simplicial, whatever you prefer, applied to that space. So from that perspective, maybe you're right. It's a somewhat more naive idea, right? Than just looking at the derived function. But yeah, maybe let me try to come up with a somewhat more convincing answer for the next time. So here is an simple and important theorem. Suppose that G acting on M, omega and mu from M to G star is a Hamiltonian G space. So is a Hamiltonian G space. So then you can define omega G equal to, let me better write it in the same way as I did before. So it's a form and it's a polynomial on the Lie algebra. And this polynomial has two parts. So one part is omega itself, and it's a polynomial of degree 0, plus it's a function on M, which is a linear function of X. So, and this is an equivariant to cocycle. So once you have a structure with Hamiltonian G space, it gives you canonically for free an equivariant to cocycle in equivariant cohomology of your space. And this is essentially why there is a link between Hamiltonian geometry and equivariant cohomology. Of course, we'll very much explore what we make out of it, but that's the core of it. Again, it's a one-line proof. First of all, let's remark that omega G of X is an element of CG2 of M. So why is that?
Is mu paired with X is a zero form then, is it?
Yeah, it's a zero form. Yeah. We will now, right.
I just tried to clarify.
Yes, that's right. So this is a 2 form, and this is a 0 form, and linear in X.
And the result is homogeneous, and therefore.
Yeah, so it is. So one thing is that this is in total an element of degree 2, because both contributions, they are in terms of the Cartan's complex, they are of degree 2, a 2 form, and the function which is also a linear function on the Lie algebra, and linear functions by our convention, they are elements of degree 2. Right, quadratic functions, elements of degree 4, and so on. So, and omega does not depend on X, so it doesn't have that contribution in the grading. Now, we know that omega is G invariant, so it's a good element, right? And we know that mu is a joint star G equivariant. And of course, the action on mu is a joint star. The action on X is a joint, right? So they're dual to each other. And therefore, the pairing between them is invariant, right? So that's more or less the definition of the coadjoint action. So these are the two reasons why this is a good element in the Cartan complex. And of course, we need to compute dg omega g. So this is equal to g dram plus iota xm omega plus mu x. And this is equal to d dram omega plus iota xm omega plus d dram mu x. So the first term is 0. This is because the symplectic form is closed. And this is 0 by the moment map condition. Right. So so this this finishes the proof. And as I say, this is this very simple fact, but this fact will play a major role in our discussion later on. Okay, so the last thing that I wanted to discuss today is the following story. So that's, we can say this is another example. So we already decided that HS1 of a point is a polynomial algebra in one variable, right? And the degree of that variable is equal to 2. So I now want to look at a non-abelian example. Let me put G equal to SU2, right? So if G is equal to SU2, we know that G and G star as vector spaces are simply isomorphic to R3. And the adjoint and coadjoint actions are simply the actions by rotation, right? We are rotating R3 by orthogonal transformations. So according to Cartan's theory, HSU2 of a point. So what is it, right? So these are polynomials on R3, which are rotation invariant. So if we say that in that R3, we introduce coordinates x, y, z, so then, of course, you know what are rotation invariant polynomials on R3, right? So this is the same as polynomials in Xi, which is x squared plus y squared plus z squared, right? So this is again a polynomial algebra in one variable. But now, what is the degree of this guy? So we said that the degree of linear functions, which are now x, y, and z, is equal to 2 for each of them. So the degree of Xi is equal to 4, right? So for SU2, we again get, as an equivariant cohomology of point, we get a polynomial algebra. But now in one variable, but now the degree of the generator is 4. So now, so let's ask the following question. Remember, in the abstract story, I said that if we have a subgroup H of G, then normally we should have a natural map from the G equivariant cohomology of any G space to H equivariant cohomology of the same space. So in particular, right, G equivariant cohomology of a point, there will be a natural map to H equivariant cohomology of a point. So in our example, S1 is a subgroup of SU2, and we can ask a question, right? So we can ask a question. So what is this map? To HS1 of a point. So we already know that this guy is R of X, and this guy is R of Xi. So what is this map? What do you think? What's your intuition is telling you? How would it work? Yeah, substitute, but substitute in which way? So that's right. I'm just reading on the chart. Yeah, sure. In some way, that's correct. Xi to X. That perhaps sorry, I misplaced. As usual, I misplaced my page, but okay. So that's correct. One needs to substitute. And okay, let me give you the answer and let me give you the general reason of how it works. So, right. So this map is defined by Xi, by the substitution, Xi equal to X squared, right? So Xi is a generator of degree 4, X is a generator of degree 2. So you are mapping Xi, maybe I better say mapping. So you're mapping Xi to X squared. So that's the answer. And yeah, maybe yeah, that's a little bit unfortunate, but what to do? So so that in general, it works as follows. So we know that HG of a point, this is SG star G, and HH of a point, this is SH star H, right? Now we know that H injects into G. Therefore, G star surjects onto H star, right? So this is just a natural map. Let's call it psi. So now, if we just apply psi to this symmetric algebra, right? We're just mapping each of the generators, each of the polynomials, each of the monomials. We're mapping it to H star. So actually, this map to SH star is just the restriction of polynomials on G to H sitting inside G, right? So that's a very simple operation. And then it is easy to see that the image of psi is sitting inside SH star H, and that's actually what we are doing here, right? You see, we have polynomials on R3, so we consider polynomials which are invariant under rotations. So these are polynomials in this Xi, which is just the sum of squares, x squared plus y squared plus z squared. Very good. And now we are restricting them to some particular coordinate axis. In this case, this is the x-axis. So we just restricting a polynomial in the radius square to the x-axis. So we get even polynomials in x. So polynomials which are polynomials in x squared, and that's basically it. That's how it works. All right. I think now I would need to start the new material. Let me instead just tell you what's gonna happen next time. So we now spend all the class on like defining this Cartan's model of equivariant cohomology and establishing some kind of relatively vague relation to the topological definition. So next time, what we're going to do, we'll prove an important theorem about equivariant cohomology, the localization theorem. We'll see. Perhaps we'll even prove it in several ways, because that's really one of the important results of the course. And then we'll see, maybe depending on how much time we have left, we maybe start talking about applications to Hamiltonian geometry using this observation that once we have a Hamiltonian structure, we necessarily have a distinguished cocycle, this equivariant, sometimes it's called equivariant symplectic form. So we're gonna explore applications to this case. Maybe the last comment that I want to make, and this comment will be important for us next time. So you see, we had an abstract definition, right? This definition with the symmetric algebra. And then we also transformed it into this formula where we said that symmetric algebra is the same as polynomials. Okay, this is all true. But now notice that in this concrete formula, we can actually, let's say this is a remark, we can actually think of x as simply a concrete point in G. So I can, if you want, forget the fact that it came from some polynomials. I can just say, well, I'm interested in the forms which are killed by this differential, or by this operator, Diderot plus iota of xm. So of course, what happens if I start thinking of x as an element of G, I kind of my grading, right? I was like trying to convince you that I really need to pay attention to the grading, and Diderot, it raises the grading by 1. And if you think of iota xm as a contraction operator and the linear function of x, then it also raises the degree by 1. But if now I decide to take evaluation at some point of x in G, well, it becomes an operator of degree -1. So now my degrees, they are completely off. There is only a Z2 degree. It's even or odd. However, it turns out that that's what we like in applications. That's a big thing to do. So this beautiful equivariant cohomology setup, it's a very useful setup. It gives you a lot of intuition, but what you do in applications is often somewhat more dirty. And that's this here I just indicated from what direction this dirty, but very still very beautiful and very efficient story will come from. So there, related to that, there are also some open questions in this theory, because when we kind of stop doing some really kind of Z-graded cohomology theory, maybe we don't quite understand what we're doing on the topological side. So as far as I know, this is not completely fixed. So we'll discuss it more next time. I think my time is up, and I don't know whether you have more questions, sophisticated or less sophisticated. No? So today was either too easy or too complicated. If substitute SU2 to SUN, you mean substitute, you consider SU2, right? In yeah, I think this is a general result, right? So right, that's what you do in general, right? There are different when you say SU2 in SUN, there are different embeddings of SU2 to SUN. So there will be those maps will now depend on the embedding, but yeah, that's the general result. You're looking at the injective map of H to G. You consider the dual map from G star to H star, and you're just sending your polynomials on G to polynomials on H by restriction. So that's a completely general result. So that always what happens. Okay, so then I think next time it will be somewhat more fun because we will be proving the localization theorem, and that's one of the wonders of the world. So yeah, we'll see. I'm thinking of even giving several proofs, but we'll see what happens. Okay, thanks a lot. So then I stop recording.